Hello, I'm Tom Hollingsworth, and welcome to Networking Field Day. We are here in Menlo Park, California, and we are talking to Forward Networks. The presentation that you are about to watch is attended by a group of networking delegates who are writers, speakers, bloggers, and podcasters from the networking community that have been invited to ask questions, make comments, and offer their opinions about the solutions and products for Forward Networks. If you would like to learn more about Tech Field Day, including how to become a delegate or a presenter, please go to our website at techfieldday.com. If you'd like to see more videos like this on a variety of IT subjects, please check out our YouTube channel at youtube.com/techfieldday.
Hi, my name is Behram Mistree, and today I'm going to be doing a couple of live demos of Forward Verify, and hopefully convincing you that it's going to solve some of your problems and make your lives a little bit easier. All right? So before you all got here today, we talked to a bunch of customers, we talked to a bunch of network engineers, we did a lot of testing, we did a lot of reading. And what we were looking for were examples of real outages. We wanted those to be nasty, we wanted them to be customer critical, and again, we wanted them to be real. So spoiler alert, something terrible is about to happen to this network during this presentation. Right?
I don't know if we can take it.
Built up a tolerance, it's okay.
But before we actually get to that outage, let's just examine the network a bit. What I have here is I have 7 routers, and they're all exchanging routes via ISIS. And just for a little bit of expositional clarity, what I did, I put 2 hosts on either end. One a client on the left there, and one this server on 18.10.11.2. Okay? Just one other thing I want to point out. Between San Jose and Seattle, between San Jose and Los Angeles, we have port channels. Right? And the high-level goal of this network is really straightforward. We want to efficiently and reliably send packets between the client and the server in this network. So what does that high-level goal mean? Let's try to translate that to concrete requirements. Number 1, our first requirement, regardless of whatever else is happening in this network, we want traffic to go from the client to the server. All right? Number 2, we want this network to be robust. We want to have multipath in this network. Number 3, we want all our interfaces and links in this network to be up. In practice, if we've satisfied these first 2 requirements, all that means is that the physical interfaces in these port channels should be up. Does this make sense to everybody? Is everybody getting this? These 3 high-level requirements? All right. So this is what it means for our network to be working. Now let's ask a different question. Is our network working? Today, this minute, this hour, is our network working? All right? And I'm going to try to answer that question in 2 ways. 1, I'm going to use a traditional approach with traditional tools. Secondly, I'm going to try to use Forward Verify. And so let's start with the traditional approach. All right? Again, we have these 3 requirements. 1, traffic should flow from the client to the server. How would you verify that today? I heard ping. That's exactly right. So I actually have this network running in my lab. I'm just going to execute the ping that I heard in the audience. So I'm going to log into the client, and I'm going to ping 18.10.11.2. Let's just do that now. OK. So I'm on the client, ping 18.10.11.2. Bytes are flowing. Everything's OK. All right? Number 2, traffic should flow from the client to the server along multiple paths. How would we do that today? Traceroute, that's a great option. I'm going to take a little bit of a shortcut for right now. What I'm going to do is I'm just going to log on to the San Jose box. I'm going to type show route. I'm going to make sure that I have 2 next hops, presumably out of Seattle, presumably out of Los Angeles. So let's log into that box right now. I'm on San Jose, show route. I'm going to enter through my routing table, keep going. I'm looking for that.
Someone using Tmux.
What's that?
I'm just happy to see someone using Tmux.
Tmux is terrific. All right. So again, I'm looking for that 18.10.11 subnet. And what I'm seeing is I indeed have 2 different next hops. All right? So traditional tools. Number 2, traffic should take multiple paths. Looks good. Number 3, traffic should flow on all interfaces in a port channel. How would I do that today? Okay, this one's a little bit more tricky. What I probably have to do the Seattle box, I'd run some CLI commands, check their output. For now, just for the purposes of time, I'm just going to look at that Los Angeles box. All right, so let me log into that Los Angeles box. We're right here, Los Angeles box, show route, or sorry, show interfaces LACP. Oh, got the command wrong. Show LACP interfaces. All right, and so what this command is telling me is I have one port channel on this device, AE0, and it's composed of two physical interfaces, GE001 and GE002. All right, and what I see here, GE002, receive state current, transmit state fast periodic. Great, it's up, it's running. What about GE001? Seems a little suspicious, right? Receive state, port disabled, transmit state, no periodic. Something seems to be wrong with this interface, right? So let's just check that. I'm going to type show interface, GE001. Let's try to read through some of this output. Physical interface, GE001. It's enabled, but its physical link is down. All right? So what this means is if we look at our three requirements again, what we're seeing is first requirement satisfied, those things are running. Second requirement satisfied, we ran that show route command. Third requirement not satisfied. And so using the traditional approach to get a basic answer to this basic question, is my network working? And to find a network engineer, to ask that network engineer to log into 3 different boxes, execute a bunch of commands, interpret their output, and get back to me. We think that there's a better way. And that better way is to use forward verify. Let's take a look at it now. So this is forward verify. This is the exact same network in our current tool. Oops, sorry, I got logged out. Let me log back in. So this is forward verify. This is the exact same network in our tool. And what I'm going to do is I'm just going to collect a snapshot. I'm going to press take now. And what's happening here is when I press take now, our software is logging into each of those boxes. It's running a bunch of those CLI commands to dump all their configuration, all their state, and build that model for us. So a couple more seconds, 6 devices, 7 devices, just a couple more seconds. There we go. We just did all that. We logged into those devices, gathered all that state, built our model. OK? So again, we want to verify 3 things, 3 requirements with forward verify. Number 1, traffic should flow from client to server. Simple. Just go back to forward verify. Going to click on check. Existence, traffic can go from client to server. Create check. Pass. Great. Second check. Traffic should take multiple paths from the client to the server. Let's check that too in our tool. From client to server along 2 paths. Number 2, also passing. Third requirement. Traffic should flow on all interfaces in a port channel. Now this one's a little bit different than the other 2 checks that I just showed you. I'm going to talk about predefined checks a little bit more in the upcoming demo or in the next demo. For now, let's just look here. We see I click on predefined checks, see port channel consistency. All configured port channel interfaces should successfully join the port channel. That's probably what we need to press. Port channel consistency, done. And just like we saw with the traditional approach, we had those 3 requirements. I'm going to make this a little bit bigger for you. We had those 3 requirements. 1, traffic should go from the client to the server. 2, we should have multipath. 3, all our interfaces in a port channel should be up. 2 passed, 1 failed. And what's really cool about our tool is not only did that check fail, if I click on failed, I can actually see why. It's going to tell me exactly why. On LAX, on this port channel, GE001 is down. It's not part of the port channel, even though it's configured to be. If I click on this configuration, it's going to take me to the exact line for why we think that is. Physical interface, GE001 enabled, but physical link is down. Is everybody getting this? Great. OK.
Is everything that you grab kind of a screen scrape like that? If there's an API available, can you hit an API to pull structured data back from the device and find out its state?
We would love to pull structured data from devices. That's really dependent on the actual vendors and whether they support it or not. So For instance, with OpenFlow, we pull a bunch of structured data. Frequently, for a lot of existing vendors, we actually have to run the equivalent of CLI commands and just dump it like that. Does that make sense?
Yeah, you take the best of what you can get.
But if all of you guys can twist some arms, we'd love to pull structured data.
Yeah.
The problem is we're collecting more than anybody generally has ever collected in an automated fashion from these devices, and so it's just not exposed via SNMP, via standard non-CLI commands. So we're stuck with the lowest common denominator.
And even if you have an API, it's kind of all over the place what you can get out of it. Yeah.
And we don't want to spend the time implementing an API to have to piecemeal go back and forth. Like, we want to get it all in one shot. So twist some arms. Let's get them to expose everything, and we'd love that.
It's a great question, though, Ethan. All right. And one other thing that I think is really cool about our tool, remember before we had to have that network engineer log into all of those boxes to answer this basic question? Right now, all I have to do is I have to just press this button. Take now. Our tool is going to automatically go to all these devices, suck all of that information in, build a model, and automatically run that check for me. So I can instantly answer that question, is my network working, yes or no? OK. And I just want to pause a moment to sort of think about the implications of this. Using the traditional approach, essentially what you're doing is you're betting your company on this. You're betting your company on having skilled network engineers that know what it means for a network to be working. You're betting your company on having skilled network engineers that know how to log into all these boxes, check out all these different types of CLI, interpret their output, process their output, interpret what that means. And you're betting your company on those network engineers having the time and the capacity to do that frequently enough so that you're going to catch minor bugs before they become major issues. And for the rest of this demo, I'm going to show you how that bet can go wrong. All right? And specifically, I'm going to show you how that bet can go wrong by trying to fix a problem in a network. Remember, we had this third problem that was failing. We had this third requirement that's failing. One of our physical interfaces in our network is down. And so what I'm going to try to do is I'm going to try to replace that interface. I'm going to replace the line card. But in so doing, I'm going to cause a major outage. All right? So let's just walk through some of the steps that we'd take to fix this, to replace this interface. Number one, we're running ISIS here. I don't know how many of you are familiar with it. At a very high level, while we're changing this line card, we want to ensure that we're not affecting any other traffic in this network. And if we set this overload bit, what that overload bit is going to do is it's going to tell a Los Angeles router to stop announcing any transit routes. All right? So while we're changing that line card, all our traffic from the client to the server should take this north route. Does that make sense to people? And so let's just do that right now. I'm going to log on to the Los Angeles box, set, I'm going to enter configure mode, set, protocols, ISIS, overload. All right? And so again, oops. What should we expect to see? We just set that configuration bit, and so what we should expect to see is we should only expect traffic to go across this north route, not across this south route. And we're just going to wait a couple more seconds while we're collecting all that data, building the model, and we're going to just verify that. 6 devices, a couple more. Cross your fingers. There we go, 7th. All right, terrific. Then I'm just going to do a search. Traffic from client to server. It's exactly what we see. So we set the ISIS overload bit. Los Angeles is no longer announcing the route to reach the server. We only have our traffic flowing across this north route. Does this make sense to everybody? All right, great. So step number 2, we're actually going to replace the line card. All of these devices are virtual devices, so I don't have somebody standing in a data center with a screwdriver, with a hammer, who knows how you actually change a line card, right? We're actually just going to run a script. All right? And so I'm on that Los Angeles router. I ran a script to replace the line card. And now what I want to do is I want to verify that change. And I'm going to verify that change in 2 different ways. 1, I'm going to use a traditional approach. And 2, again, I'm going to use forward verify. So I made a change let's start with the traditional approach. I made a change, and I'm just going to check now, is my port channel up? Log into the Los Angeles router, show LACP interfaces. So remember before, GE001 was down. Now we see that it's up. We can run show interfaces again. Before, physical link was down. Now it's up. All right? So hopefully we changed our line card OK. What are some other things we should check? Well, let's make sure that this Los Angeles router can still ping the server. Ping 18.10.11.2. That looks OK. Maybe we should also ping that the Los Angeles router can reach the client. Do that too. Just be extra thorough. Looks good. Again, we can log into the client. We see our pings are still flowing from the client to the server. So everything should be great, right? Now let's see what happens with forward verify. I'm going to press a single button to take a snapshot. While this is collecting, I'm just going to change one minor setting. Sorry about that. So we're just going to wait a couple more seconds. Again, what we're doing is we're logging into each of these devices, building a model, and collecting it. Now what I see here is not what I expect, right? I changed this physical interface. I thought that everything was fine when I just verified it with the traditional approach. But here I'm seeing a check is failing. And that check is my multipath check. All right? Now, I'm sure a bunch of you have context for why this is failing. But for just a second, pretend that you forgot all of the little steps that we just went through. And let's try to actually use our tool to figure out why this check is failing. All right? So remember, one thing that's really cool about the Forward Verify platform is that not only do we tell you about how your network is working now, we can tell you about how your network was working in the past. And what we can do here is we can see in our check history, oh, this check was failing here. Oh, this check is failing now. But it had been passing at 3:27 p.m. All right? And what I can do then is I can look at all this config, all the state that we pulled in, and see what's different between now and 3:27 p.m. So I'm just going to do this comparison here. I'm going to scope it to just config. All right? And what I can see over here, there's no yellow line, 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 no changes for all that config, except for the Los Angeles config. I'm going to click on that now. So I see my Los Angeles config. Probably not these timestamps that caused the problem. Let's keep scrolling through it. We still have our overload bit set, right? And so what that means is because that overload bit is set, if we go back to checks, oops, sorry. What that means is because that overload bit is set, again, the Los Angeles router is not announcing any routes to the server, and we just have traffic going across this north route. Do people get this? Are people understanding what's happening here?
Yeah.
All right. So again, with a single button press, during my service window, I saw that transit traffic was disallowed, and I was able to fix that problem as soon as it occurred. In contrast, with the traditional approach, I didn't see it, I didn't notice it, I had this latent misconfiguration that is now festering in my network. What are the consequences of something like that? What is the consequence of this latent misconfiguration where traffic is no longer flowing across the south route in the traditional approach? What makes this network with Forward Verify with all these blue links better than that? Well, let's see what might happen. Assume for a second you had a fiber cut along your north route. What's going to happen? Forward Verify approach, traffic's just going to take your southern route. You're going to be okay. You'll have to fix this, you'll have to fix the fiber channel, but in the meantime, traffic is still flowing from your client to the server. In contrast, the traditional approach, no traffic is flowing, you have an outage. We can just simulate that really quickly. Again, virtual devices. Have my fiber cut. Traffic had been flowing. It's no longer flowing.
So this was really neat in how the policy was that you had to have multiple links. Are you able to kind of add even more checks that I could say I need 40 gig of bandwidth on those paths?
So we don't have a check like that currently. That's a great question. We don't have a check like that currently, but so many of these checks and more checks that I'm going to show you in just a bit have been inspired by customers. And so if a customer comes to us and say, we need this, we'll definitely think about adding more checks, adding more tools to make our customers' lives a little easier.
And we have the data to do that particular check today, so we could certainly build something like that.
Can we talk about scale for a minute?
Please.
How many devices can be supported and continually refreshed? Are there limits to things like lines of code in a configuration, that kind of thing?
We've verified our software on scales of thousands of devices. We have customers, we pulled data from their devices, which have over 400,000 lines of configuration.
And does that impact running tests or how often you can do your polling, anything like
Are
that?
you saying running tests in our system?
All of it,
Yeah.
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 This is all very quick, but it's a
Sure.
small set.
No, of course. That's a great question. So we are going to be limited to how fast we can pull configuration from devices. Ultimately, we think that there's a lot of value from just having configuration that you've already taken snapshots from, and you'll also be able to take snapshots more frequently. David, do you have additional thoughts on this?
Yeah, so there's actually a great Twitter question about this. So the collection time certainly is generally proportional to the number of lines of config or state that you're getting out of the devices. And this is because these commands are typically meant for humans today, and so they operate at human timeframes rather than automated collection timeframes. So
Yeah, and just to be clear, you're doing a couple of things. You're not just yanking a config, you're also doing SNMP queries.
not today, just CLI
okay.
commands. Yeah.
Okay.
But they're doing more than pulling the config.
But doing more than pulling the
Park
config,
tables,
yeah.
switch tables, and route
Yeah, think of
tables.
it as polling. Yeah, we're doing more. Yeah, exactly right. So show routing tables, show ARP tables, everything that's in the device that defines its behavior. So today, a number of these paths are just not optimized because the engineers at the vendors haven't spent time making those fast. In our testing internally, we've played with some of the development environments that allow you to put plugins on the devices just to see how fast we could get it out if we did it in a more optimized fashion. And we've been able to get it out nearly instantly. So if we can get the vendors to build in faster egresses for this data, that time will be driven down to nothing. And then to sort of follow your next question, our processing time certainly is proportional, right, to the complexity of the network and how many things are in the devices. So this is an easier network. It'll take a little bit longer with the size of what's in the config and in the state, but we also scale out horizontally. So if you have some deadline for how quickly you want to process, you can put more hardware on it and it'll take care of it.
Okay, so that was the next question. So we can parallelize queries by scaling out this architecture.
Everything, processing, queries, all of it. Yeah.
So you can build it as big as you need so that you've got the responsiveness you need to match the size of your network.
Exactly right.
Yeah, and it probably just costs money,
It's just money.
right? Okay.
Can't take it with you.
So how many racks of equipment do I have to do that?
Depends on the size of your network. We'd sit down and do some sizing with you, but we try to keep it obviously as efficient as possible. We also have a cloud offering, so if you don't want to do that, you want to throw the processing to us, we're happy to do that, and all you need to do is run the collection client locally. That's it.
Well, what's the largest network you've queried?
We are in production with hundreds of devices today, and we're busy scaling that up, and we've certainly done queries on 1,000.
Well, what's the collection time on hundreds of devices?
It's gated. It's gated by the slowest device you're collecting from because the collection happens in parallel. So if all your devices are quick, it'll be quick. If you have a couple little slow, they'll drag the heels a little bit.
So for that couple hundred node network you're working on, what's the size of the server and resources that are being used?
Brandon, do you recall the size of that today?
So the typical deployment we do is a single VM. So going back to an earlier question, we tend to ship an OVA, right? You can deploy it on the hardware you want. And so we've seen people deploy it on as low as 16 gigs for smaller networks But we like to start out at something closer to 64 gigs. But we've seen much larger than that actually, and we're able to take advantage of more memory and more cores within a single device as well.
So starting at 4 vCPUs, 8 vCPUs.
That's a starting point, yeah.
It's really just how fast you want to process. Like more hardware means faster results. It's not necessarily going to prevent you from collecting and processing. If you have a lower spec equipment, it'll just impact the user experience.
Obviously, a lot of the data with your snapshots doesn't change over time. So are you doing some data deduplication to make sure that your footprint stays the same? We don't have to have a ton of storage to maintain
100%.
this.
Yeah, and we certainly also cycle these out, the snapshots over time. So there's a couple things we'll just kill them once they start to fill up the disk, or if you want to suck them out and archive them somewhere, that's all via the API, you can do that. But they're just text, right? And text compresses incredibly well. So the amount of state that is that, like the disk space per snapshot is really small.
Does this make sense to everybody?
One last thing on the resources. Is there any special I/O requirements on the resource side? I mean, since you're talking compressing text, I'm guessing there's not a heavy-hitting.
We
MySQL or
encourage
Postgres
SSDs, but it's not a strict requirement.
So what did we see in this demo? Well, we showed how forward verify could have prevented outages. We saw an issue during our service window that we could have fixed instead of having latent misconfiguration in our network just festering. We also showed how forward verify simplified diagnosing real problems. Right? Because we had historical snapshots of our network, its behavior over time, we were able to quickly determine why our behavior had changed, what line of configuration caused that. Okay? And I just want to take a quick minute to bubble up here. Today we're asking a lot of our network engineers. We're asking them to never forget. We're asking them to never get tired. We're asking them to always be available, to triage issues in the network, and find point solutions to specific problems that are happening. We believe that Forward Verify is a terrific platform to allow those network engineers to be more efficient and more effective. Those network engineers can ask whatever checks they want with Forward Verify, whenever they want, however frequently they want, on whatever networks they want. And that means you're going to get more stable, more reliable, more robust networks.